Welcome back. So yesterday we discussed about the working principle of GPR and what is the importance of GPR, why we wanted to do, and what were the outcomes. Okay, and this was the last slide where we were discussing about the utility mapping. And as I told that since the infrastructure development is on very high scale in India, this type of mapping is getting more and more common in most of the regions, and wherever. So we are coming up with in smart cities mainly. So there we need this type of surveys. Now this type of surveys are required because in most of the occasions we don't have the subsurface utility maps available with us, and if we have to put, for example, any flyover, and then piers have to be or the columns have to be put there. So we may not, we should know that what is the utility under subsurface, and that should not be punctured. So as I told that the beauty of having the 3D profiles are that we can have multiple slicing, and at what depth the particular structure or the utility lies, that also we can know, and even we can know the depth at which it goes, plus the dimension of the particular utility or a structure. So further we will just try to see that what we have gain in this. So we have, for example, this is another profile which shows the utility at different depth based on the hyperbolas. And as I was mentioning, that you can also try to understand that what is the direction or the alignment of the utility. For example, here if you take this hyperbola here, this one here, and we are having different slices, okay, at different the interval in terms of the vertical section. So you can connect, and then even manually you can do with your own this thing, but if not, then even the software can help you in putting this actually. But you need to identify the features in this region, okay, like what I have shown. So this is one advantage of 3D, and also the depth. So you can easily make out and say that until this depth, below this you don't see the utility. So utility is within this zone actually, in terms of the depth and all that. Okay. Now little bit more about that, what parameters you can select, and depending on the terrain in which you are doing the survey. So and what is the desired depth. So depending on your target depth and the area or the terrain in which you are mapping or conducting the survey, you can use different modes. Okay. So here, for example, in this system, and as I told, there is another system which is SIR 4000. We can have different scanning modes actually. So like terra search is there, concrete scan, structural scan, utility scan, geology scan. Mostly in this scans, okay, the utility scan, structure and concrete, there are few very like fixed parameters which have been input by this within the system. But in this one, this is what in 4000 we what we say is the expert mode. Okay. So the terra search and the expert mode here are the same. So expert in terra search, you can modify your requirements or the parameters which as per your desire and depending on the experience. Okay. So we'll briefly discuss that what are those parameters while collecting. So if you see the screen, this is what it will look like actually. So this is the first stage, and then first of all we need to be very careful about that what is the wiggle we are getting here, that is also known as the UO scope. So it should not shoot up on very outside the range. Okay. If such shoot ups are there, then we should try to reduce the gain, or we can try to change the parameters like what we are having the dielectric constant and all that. Okay. So in short, this is what this the system you will see, and mostly we'll try to collect the in continuous mode, and so it will be continuous mode, and then another one is that in the metric system, so in meters per we will say. Okay. And also, so that is the horizontal, as well as the depth section will be in meters. You can also look at in the nanoseconds also, that also you will be able to see here. So this is what we call the depth scale. If you want to see that, this is all in this is in centimeter, but mostly we take in meter actually. Now the first part which we have to be careful is that what is the frequency range you are using. Here it is 400, and the 400, or maybe you can use a 200 megahertz antenna, and then another system what we are having is with the 350 megahertz antenna. So this is one, but usually another one here you can put here is the 400 megahertz also. So 400 megahertz, as I told, that this is being used for the shallower depth. These are slightly deeper, and this is also again we can go up to 6 meters or so comfortably. So we have different parameters here, like so radar signal here. So 400. Then what is this T rate, mode distance? We will just try to see that. So other than that, the antenna transmission rate in kilohertz, that is your T rate, transmission rate is there, and high transmit results in fast collection of data. Okay, so if you do that, then that system allows you to collect in the faster mode. Okay, and sample here is this one here. Okay, so it goes in a like a range of like 250. Then you are having then 256, 115, 12, 124. So this is each scan curve is made up of numbers of data points known as samples. Samples are directly proportional to the smoothing of curve and vertical resolution. So this will depend again that what type of data in terms of the resolution you are trying to collect. Okay, so mostly we try to collect in this one. If you want to collect very high resolution data, then you can increase this the sample per scan, but that will make your system slow, and you also need to move on this move the GPR on the surface very slowly. Okay, so this movement will be restricted if you increase the number of scan, okay, per second. Then the format is okay, fine, 8 bits or 16 bits. Mostly we take in 16 bits. It is recommended, and the range, as I told, that either you put it in this range mode, that is time window, in nanosecond. This again you will take in two-way travel time. So the waves propagating and received back. Okay, now that will also like higher the range allows the deeper penetration. So if you increase the range, you will be able to penetrate deep, but depending on the terrain and material that you will have to judge based on your wiggle or maybe the O-scope what you are getting. Depending on that, you can do that. Okay, and the rate is like what we are talking about. Rate is here. So rate is number of scan that will be recorded per second. Okay, so that also you can again set. Okay, the rate should be set high in case of using the survey wheel. So if you are using the survey wheel, then the rate has to be higher. Otherwise, there is another method also. What we do is the point method. Okay, so you, like for example, you have kept your system here and then you have moved here again, and then you have collected the data. That is your point mode collection. But mostly if you are connecting the survey wheel, then you are going to have, like, you can keep the rate a bit higher, and that will allow you to move faster. Okay, then we have usually we give this IIR low pass filters that allows the frequency lower than the entered range. Okay, so it will allow the frequency or the frequency lower than what we have entered. So mostly in 200 megahertz antenna we take 550 and 600 like that. That is a high pass. Then the high pass filter is it allows the frequency higher than the entered one. Okay. So whatever you have entered, the frequency that will be limiting that the portion of the data collected. Now stacking is also important, and that is mainly used for the noise reduction. So high frequency noise reduction technique, smoothing high frequency features and attenuate low frequency features. So this is what we do stacking mostly. We put stacking which is around like in 2D around 13 to 14, and if you are taking 3D then we put 9. Okay, so these are the values which we have also with the experience we have fixed up that in this type of and particular terrain what type of inputs we have to put. So then dielectric constant, this component reflects the velocity of the radar wave moving through the material, and dielectric constant is inversely proportional to the depth of penetration. Okay, so this is again an important point along with the frequency of the equipment. Now to acquire the better results, pre-processing should be done by putting respective acquisition parameters. So these are the parameters which usually we use, and then and as I told, you can collect the data in 2D and 3D. So okay, so 2D if you have the like for example the surface here, then 2D you will take in one direction. Okay, whereas in 3D, so this is 2D you are taking in 3D. Suppose this is the area you are having, then you finalize that okay this much grid I want to do here, then you measure the grid and then you give xy and the starting point 0 0 and then keep collecting the data in both the direction. You can also go like you can divide this every 50 centimeter or every 1 meter you can collect the data, and you can go in zigzag way. Okay, so you can collect the data in this fashion. Okay, and then after finishing this you move in this direction. So this will give you a pretty good handle like to see what is exactly there in the subsurface. So this is a instrument with the 400 megahertz antenna. This is 400 megahertz antenna we are using, and again as we were talking about, this is the survey wheel actually. Okay, so there is another one. So this is the survey wheel, and then the data has been collected over here. This is the model which we are having, sir, 3000. So this is the part which we did in one of the archaeological site in near Bareilly. Now I'll show a couple of results what we have obtained using the GPR. So initial aim using GPR was mapping subsurface deformation. This is what we were doing for the part of like as a geological mapping, and then to locate the mostly the ancient structures here. Okay, so that what we did. So for example, this is from Kutch, Gujarat. So we found some deformational feature along the cliff, but we wanted to do this survey here. So this was been done. The GPR was been moved on the surface, and we wanted to go deeper and see that what exactly the deformation has to tell us actually here. Okay, so this is the profile which we collected, and based on the discontinuous and warped reflections, you can easily see this that there is warping here. So this based on this we mark the faults, and this is what are the arrows are showing the fault plane. Okay, this is the section 2D section we are looking at, and then we open up a trench here. So this black box broken line with the broken line shows the trench area. So we excavated the trench, and this is exactly what we see here. Okay, so you can match easily. So this one is over here, this fault, and this fault which is running here is exactly which you can pick up along in the plane here. So we were able to match what we see in the GPR. Similarly, another exercise we did in Himalaya on the left bank of the Bias river, and here also what we did was that we open up the trench after doing the GPR part. Okay, so this is the trench section. The GPR was when the data was collected initially. So this has eventually reduced our time frame and also the cost of excavation, because we knew that where exactly we want to dig, and the same case goes for the utility mapping, or even for the excavation, which may be followed after the GPR survey in archaeological sites. So this is exactly what we saw. This is the plane here, the fault plane is here. Again, the similar type of the conditions we have applied here, like we use the warping of the georadar reflection as well as the sudden discontinuation of the georadar reflections were been considered to identify or infer the fault plane. And this again, the dotted line what we see is the trench section, and exactly it matches with what we saw in the GPR. And this place is again in this same area, not exactly the same, but quite little bit far, maybe 2-3 kilometers away from the first site which I was showing. Now here the issue came was we wanted to do the geological investigations here by digging trenches and all that. Then and according to us, this is the fault might probably passes through this area here where the arrows have been marked. And when we were discussing with the local villagers, they told that there is an pipeline, water pipeline, which probably was been put way back in this region. Okay, so that should not be disturbed, because otherwise the many villages will face water problem. Okay, so we said we have the instrument which will tell us where is the pipe exactly. Okay, and then we picked up the pipe. So this is the reflection of the pipe here, and it was not very deep, it was been kept shallow. So we avoided this area and we dig the trench over here only in this portion, and this is the part which is marked here after the topographic corrections. So pipe was way below the scarp, and then we open up the trench, and you can see that it exactly matches what we see in the GPR profile. We also did 3D of this area, and that helped us in identifying that which portion of the region should be excavated for more better to get better information. Okay, that also was been done. Okay, so these are the multiple profiles which we were able to cut and slice in vertical section. Okay, then another exercise we did in the at the archaeological site in Humayun Tomb, Delhi, and this is close to the Nizamuddin railway station. So I probably I'm having few slides of this, but the information which we got and what they wanted us to do is they say that this is the monumental structure here in the center, and at a particular location they were having the earlier they were having the enclosure wall. Okay, so they're like in boundary wall, but now there is no signature on the surface. So that was another aim which they asked us to do. Okay, so we started our survey, and at some locations we were able to pick up the signatures of that. Okay, so this is what we found as from the like one of the survey which shows that there is a platform here, and then probably there is a water pathway. So what we found was that there is a platform and on either side, and probably this we interpreted as a water pathway, and these are most common features in Mughal gardens mainly. And we were also able to fix up that at what depth we are able to see this, and like up to 2.5 meters or 3, and below that we don't see the structure. Okay, what we have marked the platform and all that. Okay, and similarly, so this is what our interpretation is, and this is usually is been seen in most of the gardens, okay, in which were been constructed by Mughals, okay. So there will be pathway in between and all that. So probably this is indicative of that, okay. Now about the enclosure wall, as I told that they gave us the distance, that at what distance probable enclosure wall would be there, but on surface there was no indication. So what we did, we planned this survey like that, considering that if the wall is move in this direction, then we should have the reflections if we cross the wall at this particular portion, okay. But this was again and tentative measurements which they gave, okay. So we did GPR and we were able to pick up clear indications of this hyperbola and flat plateau and then sloping reflections, okay. And this was not only at one location, all profiles what we did, we were able to pick up this, but this was not enough for us. So we tried with 3D and we were able to see clear indication of prominent reflections that indicated that this is a wall structure which extends in particular direction and the depth. So we interpreted that this is an enclosure wall which they wanted to identify, and this goes up to 1.5 meter or so, and around 2 meters we were not able to see that actually. So this is how, so this could be, and this type of enclosure wall was there in the past, okay. Now another part, we were also able to pick up the crisscross relationship of the structures, because one we were able to see here, this is the wall structure here, but another one was here, okay. So next interpretation, if you see, that is what we have marked, okay. So probably this was the another wall along with this lump wall, or maybe the brick bads we see here, so might have collapsed, and that is one of the reason that why we see this crisscross. Again we were able to see at the depth that it doesn't extend, okay. Now the last one part which I would like to mention here was Aichhatra, and in Aichhatra we did at multiple locations, but one of the locations here where we did outside the fortified structure, and Aichhatra is a very old ancient site which flourished till 1200 to 1300 AD, and so here we did outside the structure, and the initial without processing the raw profile we were able to pick up something like this, but after processing what we saw is a very clear cut depression here, and with that the excavation was been done, and you can see that both were been compared. So this is the feature you see over here, okay. So this is what the best you can do with the GPR and you at applying for different, because it is a non-invasive technique, you don't need to go for digging initially, but at least you can mark precisely your utilities and the structures which are present subsurface, okay. So with this I will end this lecture, and more you will learn during the practical, okay. So lab part which we will do, we will record that. Now one more lecture which I will be giving will be on the OSL dating part, and that again will be followed with the by the lab, okay. So till then, goodbye, take care, thank you so much.